Today is February 9th, 2012, and this is AP Statistics at Berkeley High School. And let's finish up Chapter 10 with a discussion about comparing two means from two groups or populations. All right? Whoops, how come we're not going forward? There we go. So we're going to start out by again talking about what is the distribution of the difference of sample means looks like, similar to what we did in the previous section. Because when you start drawing from two distinct groups or two distinct populations, that distribution has a particular shape, center and spread that we're going to exploit. We're going to learn how to do some calculations based on the distribution of difference between sample means. Then we're going to start diving into the inference portion. What does it mean to do a collection of samples and then try to make a statement about what's going on at the population level? We will talk about the use of the two-sample T procedures on your calculator. That's going to be listed as the two-sample T. And then we'll talk about interpreting that output from the calculator, and then finish it off by saying, okay, what's the whole four-step process look like for these particular ideas? So, first things first. I've got two distinct populations. Probably the easiest analogy to look at is boys versus girls, men versus women, American versus European, Michigan State versus Michigan. You can take two distinct populations and you ask yourself the question, are these groups different in some way? In some way that we're measuring using a quantitative variable. Are the people at the University of Michigan taller than the people at Michigan State, for example? I don't know why anyone would ask that question, but it's the kind of question that we could answer using the procedures we're going to talk about today. All right? So, we come up with this idea that I can find out whether the people at Michigan are taller by measuring the height of every single person at that campus. And when I do that, I get a value that I would describe as a mu, a population mean. I could do the same thing for all 45,000 students at Michigan State. And I would get their average height, and that would be a mu. And I can answer the question, the average height there, the average height at Michigan, who wins? What's wrong with my scenario?
Can't measure everybody.
You could, but it's costs too much money, takes too much time. So the question is, can we reasonably come close to the answer by doing sampling instead of doing measure everyone on both campuses? Right? Well, in order to answer that question, we've got to go back and say, well, what would it be like if we had perfect knowledge? What if we actually knew mu? What if we actually knew the two mu's from the two different areas? And we talked about taking sample after sample from those two groups. We wouldn't expect every single sample to be the same. I'm going to look in particular to what would happen if I took sample 1 from Michigan, sample 1 from Michigan State, found their average, and subtracted them. And I got a difference between those means, those two sample means. And what if I did it again? What if I did it again? What if I did it for every possible sample from each of those universities and looked at the differences every single time? Well, the big picture is that these samples will vary, but each of them is a predictor, an estimate of the mu, the population mean. That sample is going to be a predictor or an estimator of that mu. And we'll use, again, mu to represent the idea of the population level, which we hardly ever get. We use x bar to represent a sample mean, which is very accessible. All right? I think we go from here. We're going to use some things back from Chapter 7, just some reminders. A reminder that whenever we pull samples out of a distribution that's already normal, that distribution of sample means will also be normal. Second thing, if we pull a sample out of a population that's not normal, the distribution of those sample means, as distribution of X bars, can be normal as long as the sample size is big enough. The central limit theorem. So, when we talk about the distribution of X bars, we've got the shape nailed. It's either going to be normal because the population is normal, or it's going to be normal because the sample size is big enough and the central limit theorem kicks in. What about the distribution of the difference of sample means, where we're pulling two of them? It ends up being the same rule. The shape of the distribution of the difference of sample means is normal if both populations are normal, or if both sample sizes are bigger than 30. Right? Why don't you get your scaffolding sheet out and go ahead and double check that against the conditions part of your scaffolding sheet. Let me guess. Anatomy test today. Is that right? I hate Scrumsy. Tell him that. Tell him stop butting into my time. Really? Of all the people on the staff, I can take him. Oh yeah. I'm from Detroit. I'm done with this guy.
You guys have the.
I can beat Skronsky, and I could probably beat Nadeau.
Maybe.
Maybe. All right. Okay. So what about other things besides the shape? We said we've got the shape nailed. If populations are both normal, the distribution of the difference of sample means will also be normal. What about the center? Well, let's do an example and talk about what do we think is going to end up happening. Imagine that we have two populations. A population of 10-year-old girls, and their heights are normally distributed with a mean of 54.6 and a standard deviation of 2.7. Let's say we have a distribution of 10-year-old boys. Their heights are also normally distributed with a mean height of 55.7 and a standard deviation of 3.8. So amongst 10-year-old boys and girls, it looks like the girls are taller at that point.
That's a pretty big standard deviation.
But there's more variation amongst the boys. I remember being on the low end of one of those standard deviations when I was growing up. It was very sad. All right. So what happens if we take and look at the distribution of difference of sample means? Imagine that we take all of these X bars from the female population. We take average after average, and I think we're doing a simple random sample of 12 girls. What happens if we take sample after sample of boys and got their average height and map them out? Oh, those distribution of sample means, both of them look approximately normal. What's the last graph? The last graph is take a sample of females, take a sample of males, find their two sample means, subtract them. I get a difference of sample means, plot it. Another sample, subtract them, plot it. Do that again and again and again, in this case 1,000 times. That distribution looks normal. It should, because it's being pulled from two normal populations. This distribution looks to be centered about, well, they say the center of that is 0.7. That center of that difference of sample means is about 0.7. Why? Well, again, if the female's average was, what, 56.4, and the boy's average was 55.7, do we see where that 0.7 is coming from? Okay, so it looks like the center of the distribution of the difference of sample means. This is the first part of the class. Too many prepositions. All right, is centered about where the difference of the two population means are. All right, and then lastly, it's got a spread. The spread isn't very meaningful for us right now, but we can make sense of it based on some work that we did earlier. Let's move on. Now, based on this fact that I think we did back in chapter 7, the mean of sample means ends up being the difference between the two population means themselves. 0.7 in that case. Here's the bigger point. Okay, we have that old formula as well. Variance of x plus y is equal to variance of x plus variance of y, if independent. Well, if you take this idea forward and you talk about the variation that would happen in sample 1 and in sample 2, and you follow that forward, you end up with that ending statement, that the standard deviation of the distribution of the difference of sample means ends up being the square root of sigma 1 squared over n1 plus sigma 2, sigma, typo here. That should be a 2 there, and that should be a 2 there. But the big point is, that formula is already given to you. Would you go check on your orange sheets and see where that formula is? It's on the formula sheet with the squares, and it's under 2 samples, because we have, again, 2 samples from 2 distinct populations. I want to make sure you all can find that. Is that good? Found it? All right. Square root sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Okay, that being said, that's great if we have population level knowledge. Tomorrow, when you take your quiz, there just might be another question like there was on yesterday's quiz, where I give you population level knowledge and say, okay, tell me some things about this distribution of differences of sample means. There's the go-to formula for its spread. There's the go-to formula for its center. And then what's the other third thing that we always talk about when we talk about distribution? Shape. And the shape is normal as long as both populations start normal or both sample sizes are big enough. All right.
Are we bringing back the 30 rule?
This is, okay, the 30 rule never left us. It's just remember the 30 rule, which is the one that goes along with okay. The 30 rule is about distributions having to do with means. That other rule that we've been using for normals all had to do with distributions of categorical data which we measure using proportions. So we have to say, are we in a proportion world? Are we in a mean world? Are we in a world where we think of categorical variables? Or are we in a world that has to do with quantitative variables? Only in the quantitative world, only in the world of means, does the central limit theorem and the 30 rule come into play. We're in that world right now. Got it? Mm-hmm. All right. The other world is what? The 10 rule, right? At least 10 successes, at least 10 failures. If you want to give it a name. Right. All right. So here's the complete summary then. If we know a population's mean, if we know a population's standard deviation, thank you. If we know a different population's mean, and we know a different population's standard deviation, if we know the two populations' shapes, we know everything about the distribution of the difference of sample means. Centered at mu1 minus mu2. Spread of square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Shape is normal as long as both populations normal, as long as sample sizes are big enough. One or the other. Don't need both. There's your equivalent to the page 1 part question from yesterday's quiz. That's the foundation on which we build the inference part. Can we go on? Yeah? All right. Let's go on. All right. So I'm going to tell you the girls are normally distributed with 56.4 and standard deviation of 0.27. I'm going to tell you that the heights of the boys are centered at 55.7 with a standard deviation of 38 or 3.8. I'm going to do a sample of 12 girls and 8 boys, and I want to know about the shape, center, and spread of that sampling distribution. Let's start with shape. Normal. Why? Because both populations are normal. Okay. Center. Point seven. Why? And actually, what I need is I need notation, and I need answer. Okay, you gave me the numeric part of the answer. What did you answer? The mean x bar 1 minus x bar 2. Okay, the mean of something, the mean of the distribution of the differences of those sample means. Okay. Lastly, spread. What are you about to give me? You're about to give me a sigma. A sigma of what? Sample 1 minus sample 2. As if we did again and again and again. And this one's ugly, right? Square root of 2.7 squared divided by 12 plus 3.8 squared divided by, our sample size was 8. And that's some number. I'd really like someone to come up with that number for me. Well, I know, I'm sorry, you know what, I'm an idiot. Well, not a big idiot, small idiot. It's very short. I'm supposed to be demonstrating how to do that on the calculator for you. Because it's awkward. It's a difficult thing to key into the calculator. I should be doing something like second square root, so we get a square root symbol. And again, with the new calculator, I'd like you to do alpha 1, so we get that fraction. And it was 2.7 squared, and then underneath it, it was 12. So you've got an answer to compare mine to, right?
Yep.
Yeah.
Oh, I didn't mean to do that. Delete, 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 delete.
You have to scroll over a couple times.
Delete that. There we go, plus. Second, alpha F1, another fraction. There we go, 3.8 squared. And then down here for 8. We good now?
Yeah.
All right. So we're good there? And again, if you use those fractions inside, you get something that looks like the way you would write it down, and you can compare it. If you do it with just parentheses, I have a hard time doing it correctly. So anyway, so it ends up that we have a standard deviation of 1.55. And there's we have it. Okay. Now, what's the kind of question that I could ask you about this? I do a sample. What's the probability that the boys are taller? I do these two samples of these two sides one time. What's the probability with those particular samples that I'd actually end up getting an average height taller for the boys than for the girls? Well, let's put all the pieces together. Here's my normal distribution. It's centered at 0.7. It's got a standard deviation of 1.55. Now, there's a line somewhere on this axis in which the boys are taller than the girls. It's not here. This would be like I did an absolutely average draw from the girls, an absolutely average draw from the boys. Girls are taller at this point. But at some point, at 0, the boys and the girls are the same height. And some portion of the axis, down here, the boys are taller. On the other side of this line, the girls are taller. Can I calculate the area under that curve? Should be able to. Z is equal to 0 minus 0.7 divided by the standard deviation of that distribution. This is going to be something like negative 0.5 or 0.6.
Negative
0.5. Okay? And then what do I do with that? I change it into a probability statement. The probability that Z is, and I'm going less than, negative 0.5, or negative 0.45, and then I look it up on our tables. There's my table. Z value less than negative 0.45, and it looks like there's a 32% chance, or 33% chance as I look at that intersection. So, the probability that that would happen by pure chance alone, about 33%. All right? It should sound really very much like the kinds of questions that were on the front page of yesterday's class. All right. Let's move on. Okay, now. Hi, Paul.
Good morning.
How are you today?
Fine, thank you. How about yourself?
It's fine. How many people are still in the hall? Who is it? Who's still in the hall? Emily? All right. So, let's go back to a previous fact, and now we're going to look at the flaw in the plan. And that is, it's on the question of spread. The standard deviation of the difference of sample means is this formula. But the problem is there. Sigmas. Sigmas are population standard deviation. And we don't know them. We need SE. I could not have said that better. We need standard error. We don't know sigma, so we're going to take our best guess at what sigma is. So we're going to say the SE of x1 minus x, or x bar 1 minus x2 ends up being this whole formula, but with s's instead of sigmas. Again, the difference between an s is coming from a sample. Sigma comes from a population, and we simply just don't know what's going on with the population. So, that being said, if we have to settle for standard error instead of standard deviation, that also means that we have to make one more adjustment, and that is we can't use Z anymore. We need to use T. So it's going to end up happening that because we don't have all the numbers we'd like to have, we instead have a procedure that's going to be prone to error, or more error. That error shows up as a t distribution with more stuff in the tails. All right, so let me erase all that stuff that I wrote, and let's see what the publisher has to say about this. All right? So when the independent condition is met, we have this great formula for the standard deviation of the difference of sample means, but we can't use it because we don't know what sigma is. So instead, as Paul has said, we're going to use the standard error for the distribution of difference of sample means. And if the normal conditions are met, then we can measure, then we know that the distribution is roughly normal shaped, and that means we have all the preconditions met to be able to use the t statistic. Anyone need more time on that slide? All right, hearing none. So our final thing then is the t statistics calculation. The thing I'm circling in blue is the mean of the distribution of difference of sample means. The thing I'm circling in red is a statistic that we get from doing two independent draws from two distinct populations. But it's a statistic. So the top of that fraction is still that general form of a statistic minus a parameter, and then divided by, this time in black, the standard deviation of the statistic, or our best guess at it. So it still follows the general form of all critical values. Statistic minus parameter divided by standard deviation. Now, what's so special about the t-distribution that made it fundamentally different than the z? It had to do with the initials df. Degrees of freedom. Remember that there's not one t-distribution, but rather many t-distributions, each one varying a little bit based on the degrees of freedom. And degrees of freedom had a great little formula. It was n minus 1. But now we have two samples. What are we going to use for degrees of freedom now? N minus 2. It's actually a very reasonable guess. It's wrong, but it's very reasonable. Actually, it's going to come. Actually, N minus 2 is going to show up in another chapter. Okay. Well, actually, the theme that we've had with t distributions for quite a long is like that the word expression most conservative, and the answer is going to be the degrees of freedom that we're going to use is, ready? N minus 1. Well, n1 minus 1, or n2 minus 1, whichever one is smaller. I'll say that one more time. The degrees of freedom that we're going to use is n1 minus 1, the sample size from our first population, or n sub 2 minus 1, whichever is smaller. And that again follows that theme of the t-distribution. We want it to be very conservative. We're not willing to take chances. Now it ends up that your calculator is not going to use that formula. No, it's okay. There's a very, very complicated formula that will give you a very aggressive degrees of freedom. And your calculator uses that. Typically, the differences are not so great that they matter a lot. But I just don't want you to get freaked out when you use the calculator and you see degrees of freedom is 15.6. Again, they're using a very aggressive degrees of freedom. But when we're doing our calculations by hand, we're going to use that rule. Whichever is smaller between n1 minus 1 or n2 minus 1. All right. And there's them saying the same thing. Two-sample t-statistic has approximately a t-distribution. We can use technology to determine degrees of freedom, or we can use the conservative approach using the smaller of n1 minus 1 or n2 minus 1. I think we got that point home. I think I thoroughly understand it. All right. That was supposed to be a joke. All right. So, what do we do in the inference pattern? We can do two things. We can do an inference test, or we can calculate a confidence interval. Confidence interval first, our statistic plus or minus a critical value multiplied by the standard deviation of the statistic. All right. T star, we already know how to read the T star values off of the T table, so that part hasn't changed. You already know how to find the degrees of freedom for these particular cases. Remember that we still have the big three conditions. We want our samples to be unbiased. We get that by random sampling. We want it to be normal, as we said before. If it comes from two normal populations, we're good. If both samples are greater than 30, size 30, we're good. Otherwise, PWC. Independent, we need the populations from which we're drawing to be much bigger than our samples. Population 1 needs to be at least 10 times greater than sample 1. Population 2 needs to be at least 10 times greater than sample 2. And lastly, we need independence between our samples. There needs to not be a relationship between thing in sample 1 and thing in sample 2. Remember my analogy of boyfriend-girlfriend, or maybe two siblings, one in each set. If we do true simple random sampling to determine the members of our sample in both cases, we'll also have independence of sampling as well. Any more time needed on this slide? This is, of course, all summarized in box 2 on your scaffolding sheet. On to an example problem. I have a problem in which we are looking at what? Trees in a forest. The Wide Tract Preserve in Georgia is an old growth forest of long-leaf pines that have survived relatively undisturbed for hundreds of years. One question of interest to foresters who study the area is how does the size of the longleaf pine trees in the northern and southern halves of the forest compare? To find out, the researchers took a random sample of 30 trees from each half of this area and then measured the diameter at breast height in centimeters. So I guess they go up to the tree right at this height and then measure around. I guess that's what that means. Comparative box plots of the data and the summary statistics for Minicat are shown. Construct and interpret the 90% confidence intervals for the difference between the heights. Okay. Now, just looking at the box plots, can you give me a one-sentence summary? It looks like the southern trees are taller. And we can say that because if you compare median to median, they win. From Q3 to Q3, south wins. Q1 to Q1, south wins. On the three best measurements of size, it looks like south has an advantage. But it also looks like on the smallest ones, they're about even, and on the biggest ones, north wins. So, how about we go to the tiebreaker? How about we say, what do we think the difference between their mean heights are? Well, here's a summary of the means, of the summary of the sample of 30 trees from each group with their standard deviations. Let's go ahead and calculate the confidence interval. The confidence interval is going to be, by the way, which one do you want to be population 1? North because it's listed first? Sure. Population 1, population 2. So this is going to be mean 1 minus mean 2 plus or minus T star, the critical value for T. Okay, let's get those T charts out. Let's figure out what the T star value is for this case. And again, remember, two issues on the T table. We need to know what our confidence level is, and we need to know how many degrees of freedom. Let's go with degrees of freedom first. Both samples are size 30. degrees of freedom is 29. So we're going to look at the degrees of freedom line with 29. Need to go to my t-table, 29, great. And then the second part is, what was the confidence level they asked us to calculate? 90%?
Yeah.
So let's look at the bottom, and there's our 90% confidence level right there. So it looks like our t star value is going to end up being 0.6 or 1.699. Hope I did that right. And now we're going to multiply that by what? Something ugly. The square root of 17.50 squared divided by 30 plus 14.26 quantity squared over 30. And there's the calculation that will give us that confidence interval. And of course, at this point, someone should say, but Mr. Fedor, do we really have to do that all by hand? What? Of course not. Where would the piece of technology which is going to help us out, where would that be for us? Okay, stats, tests, and indeed it's going to be two sample, and we're looking for a t, and we're looking for an interval, and I don't see it on the first page.
0.
Is it 0? Oh, we're saying, yep, 2 sample t interval, that's it. So, do we have data or we have statistics? Statistics. We have the summary of all those things. But if we had the raw data, we could put it in list 1 and list 2 and get it out that way. I don't know the numbers anymore. Oh, I know what I can do. I can do this. There we go. 23.7 is the mean of the first sample. Standard deviation of 17.05 is the standard deviation. N1 is the sample size of 30. And X bar 2 is the mean of the second sample. Standard deviation of 14.26. And sample size was 30. And the confidence level was 90%. There we go. So, pooled. Pooled. We got to talk about pooled. Okay, here's what you have to remember about pooled. You'd be a fool to use pool. Okay? We are never going to pool. Never, ever. All right? Now, let me tell you what pooled is in 30 seconds, and then I'll tell you why we're not going to pool. Okay? We only pool if we suspect that the standard deviations amongst our two populations are exactly the same. Why we would suspect this, I do not know. But the most conservative thing to do is to not assume that that's true. So we will never pool. We will never assume that the standard deviations at the population level are the same. So we never pool. Got it?
Yeah.
Never pool. I think that's where the Beatles were from. Never pool. All right. All right. So there we have it. There's our confidence interval. We believe with 90% confidence that the true difference between the diameters of these trees is between negative 17.7 and negative 3.9. Now what does that mean to us? It means that the northern trees, okay, this is always 1 minus 2. Southerns must have been bigger, that's why we have negative numbers. And because this particular confidence interval doesn't have 0 in it, we have enough evidence to suggest here that the mean of the southern trees is actually bigger. We think that the true difference in the mean is always favors on the southern side. Got it? All right. Come on, go back there. Okay, let's try this. Let's go this. Can't cancel that. All right, there we go. Let's see what else they have to say. Okay, now they are going to do this using the 4-step process. All we did was the step 3 part, right? Did we check the conditions?
No.
Did we state what our population and our parameters were? Okay, so let's go through this really quickly. Population. Well, population 1 was northern trees, northern long something pines, whatever that was. Longleaf pines. Sounds like a contradiction. Because pines don't have leaves. Okay, so population 1 was the longleaf pines from the north. Population 2 were the longleaf pines from the south. Parameter of interest was the mean diameter. Do we have an H naught? Not for confidence interval. Do we have an HA? Nope. Do we have an alpha? No. All right. Second, part 2. Conditions. Do we have unbiased samples? Well, they said they use simple random sampling, so we're going to say okay on that. Do we have reason to think that the sampling distribution is normal? Answer yes, because both sample sizes were 30 or bigger. And then lastly, do we think that we have independence? Do we think that there's more than 300 longleaf pine trees in the northern part of that park? Probably. I think it's a safe assumption. Okay, and then lastly, is there independence between the samples? Is there a relationship between things in sample 1 to sample 2? Now, if they use simple random sampling, we have independence between samples as well. All right. So we meet the step 2 conditions. There's their calculations. There's the same numbers. Now, what they did was they flipped them. They made the south population 1. They made the north population 2. So their numbers are positive, but they give the same idea. We think that the southern trees are bigger in diameter than the northern trees by somewhere between 3.8 centimeters and 17.8 centimeters. Yeah?
Why is the calculator degree freedom way off?
Because the calculator uses a much more aggressive degrees of freedom. The calculator will always, like we use 29 degrees of freedom. What did they say did it say on the calculator what they used for? 55. A much more aggressive. And again, I believe in your book, the formula that they're using to do that is published. And it's nasty. I mean, it's just like, I never want to see that formula. I'm trying to see if I can find it. And I'm just going to point it to you, and you're going to say, yeah, I never want to use that. There it is. Okay. It's right there. Bradley, would you say that's a repulsive formula? Kind of like it's all yours then. You can have it all to yourself. But it's a sum of the square of 2 fractions on the top, and then the sum of 4 fractions on the bottom. Only a total of 8 fractions within a fraction. So anyway, the calculator uses that because the calculator can do this really, really well. In order to get to the more important point, though, we're going to use the simpler degrees of freedom, a less aggressive one, a more conservative one. All right? How far was our answer off from the one using the table and using the smaller degrees of freedom? A lot?
Like 20.
20? Like
I
2/10?
think it was like, oh, no, I'm sorry. I thought you had degrees of freedom.
1/10.
Okay, so there's the aggressive degrees of freedom again. All right? And if I hide this, so the answer by hand is, on the low end is 383. Our answer was 393. Okay, so a tenth of a centimeter, a millimeter. I can live with that tolerance to make our calculations a little easier. All right, either answer on your test, by the way, will be acceptable. So when I do the answer keys on your test, I actually have to do every problem twice. Lucky me. All right, there's our step 4. It suggests that the southern trees are between 3.8 and 17.8 centimeters larger. All right, so there's confidence intervals. What's left? Answer significance tests. Like we did in the previous section, when we're doing a significance test having to do with 2 distinct populations, our H0 assumption is there is no difference. We believe that population 1 and population 2 are the same, having to do with this particular item. So our H0 claim is mu1 minus mu2 is equal to 0. But most often, we just write it as mu1 is equal to mu2. Now, if mu1 is equal to mu2, that means the center of the distribution of the difference of sample means is going to be at 0. We have 3 alternate hypotheses, same as before, same 3 conditions: independent, unbiased, normal. Just like in the confidence interval, we meet those conditions the same way. The t statistic is going to be x bar 1 minus x bar 2 minus the quantity mu1 minus mu2. But wait, I thought we said in our H0 claim that mu1 is equal to mu2. So that should be a colon there. So what does that mean? That thing is just a big 0. When we do significance testing, it ends up that mu1 minus mu2 is 0 because there is no difference. So on your scaffolding sheet, what you're just going to see is x bar 1 minus x bar 2 divided by that square root junk to get your t-value. All right. And remember, you can either use the aggressive degrees of freedom that come out of your calculator, or you can use the more conservative one that's easier to calculate, the smaller of n1 minus 1 and n2 minus 1. All right? Conditions. How many times do we have to see these? We got them all? Again, the only one I'm really worried about with you guys is normal. Right? Now, if we're told that both populations are normal, we're good. If we're told that both samples are bigger than 30, we're good. What about the intermediate area? Okay, here's the rule. Remember how we had 3 different standards for normal with the t-test? If it's less than 15, the sample has to look normal. Between 15 and 30, no outliers or strong skewness. And after 30, anything goes. Same thing happens here with the 2-sample test. Because typically we don't know whether the population is normal or not. If it's less than 15, both samples need to look normal. If it's between 15 and 30, both of them have to not have outliers, and both of them have to have no evidence of skewness. And if they're both over 30, anything goes. So, one other thing that can happen. What if one sample is like 8, the other one is 20? With the sample that's small, with the sample size 8, use the more strict standard on that group. The other one can use the other standard, which is no outliers, no strong skewness. So you adapt to the sample size. Don't forget about independent. And I believe the only thing left to do is an example. All right? So we got 3 minutes. We're going to go right to the end. All right? So I got 2 groups, a calcium group and a placebo group, and we're trying to find out whether calcium reduces blood pressure or helps control blood pressure. I've got 2 groups of data, and I asked the question, what's my null hypothesis? My null hypothesis is that there's no difference. We're going to assume that the placebo and the calcium treatment have the same effect. What's my alternate hypothesis? I would expect that we're looking for a decrease in blood pressure amongst the calcium group and not as big of a decrease in the placebo group. Or if group 1 is my calcium, that the decrease in blood pressure in the calcium group is greater than the decrease that we saw in the placebo group. There's my alternate hypothesis. Why is the alternate hypothesis, of course, important to us? Because that's the direction of the probability arrow in step 3. Okay? I don't like the way they write their hypotheses. I like it better with you put mu's on both sides. Check the conditions. Check the normality of each set. Since these sets are pretty small, they're 21, all we're looking for is a lack of skewness, lack of outliers. Both of the normal probability plots are relatively linear. I say we pass the normality check. On from there, we calculate our t-value and our p-value. Again, I suggest that you just look at your calculator and get those t's and p's out of there. Don't forget to write your probability statement appropriately. In this case, the probability that t is greater than 1/604. And then from there we get some p-value. And that p-value, again, from the t-table is going to give you a range. Calculator will give it. I think you're going to be okay for tomorrow. I'll give you a chance to ask questions before the quiz.